So after discussing real zeros in section 3.5, now we're going to discuss complex zeros. Complex zeros include real and imaginary, okay? And the fundamental theorem of algebra. Okay, so let f of x or p of x, whatever you want to call it, be the general polynomial function, like we did earlier, plus a2x squared, a1x plus a sub 0. Be a poly function. This time, different is it has complex coefficients. So the coefficients, the a1, a2, could be real numbers, could be complex numbers, okay? N has to be greater or equal to 1, so it has to be linear or quadratic or higher, and the leading coefficient cannot equal 0 as usual. The fundamental theorem of calculus says, the fundamental theorem of algebra, sorry. It says every polynomial function with complex coefficients. Again, complex doesn't mean all I. It could be real numbers, okay? Because complex numbers include real numbers as well. Complex coefficients has at least one complex zero. So there is no way that you have a polynomial function, whether it's linear, quadratic, third degree, or any degree, and that doesn't have 1 0. It has to have 1 0 or more, 1 or 2 or 3 or whatever. Okay, at least one. That 0 be imaginary. For instance, if you look at f of x equals x squared plus 1, this doesn't have any real zeros. From the graph, we know that. Right? It doesn't cross the x-axis, but it has two imaginary zeros. It's x plus I and x minus I. Okay? Because x squared plus 1 equals 0, x squared equals negative 1. When you square root it, so x equals plus or minus I. Okay? So this has two complex zeros. None of them is going to show on the graph because they're imaginary zeros. Okay? So what does the fundamental theorem of algebra tell us? It tells us that every polynomial function, whether the coefficients are real or imaginary, will have at least one zero. That zero could be real, could be imaginary. The linear factorization theorem is next. The linear or complete factorization theorem. It says an nth degree, any degree as long as it's one or more, an nth degree poly function can be expressed as the product of a non-zero constant and n linear factors. Those linear factors are not necessarily equal. They could be equal, but they don't have not necessarily distinct. So they could be equal, they could be different. So you could write it like this. The product of a non-zero constant, a sub n, that's your non-zero constant, and n linear factors, not necessarily the same. So the c's could be the same, could be different. Okay? So basically a degree n polynomial function will have n linear factors. N linear factors. If you recall, f of x equals x squared plus 1, a degree 2, it has two linear factors and a leading coefficient of 1, and those are imaginary. They don't have to be real anymore, okay? Let's look at an example, number 14, page 293. We have p of x equals x to the 4 plus 6x squared plus 9. Page 293, number 14. It says a polynomial is given, find all zeros, and real and complex, and then factor it completely. So to find the zeros of p, x to the 4 plus 6x squared plus 9 equals 0. This can be factored. X squared plus 3, x squared plus 3. So to find the zeros, each one of these equals 0. So move the 3 over, square root it. So x equals plus or minus I root 3. Same thing here. So there's 4 zeros and they're all imaginary. Then factor it. We know that for every 0 we have a factor. So if x equals I root 3 is a 0, then x minus I root 3 is a factor. If x equals negative I root 3 is a 0, then x plus root 3. And then we get the same thing there. And we, as expected, we expected 4 linear factors, 1, 2, 3, 4, because the degree is 4, although the zeros are imaginary, but who cares? Remember, we're talking about complex zeros. Now let's look at some results of the fundamental theorem of algebra, some corollaries. If f is a polyfunction of degree n, which means it's linear or quadratic or higher degree, then counting multiple roots separately, the function has exactly n roots. Has exactly n roots. That's a big thing, because the fundamental theorem of algebra says we have at least one zero, real or imaginary. But this is telling me if the degree is n, then you're going to have exactly n zeros, counting multiple roots separately. So if a root has twice, then you count, like x equals 3 twice, you count it twice. Okay, like here, degree is 4. There was 1, 2, 3, 4, although each root is appearing twice, but still there's 4 of them. Counting them separately, the degree is okay. This is great. So now if we're solving a polynomial equation of degree 5, we know we're gonna have exactly 5 zeros. They could be real, they could be imaginary. It could be the same 0 5 times, but still there's 5 of them. Another thing is complex zeros, imaginary zeros, okay? Imaginary zeros, like the ones with I, occur in pairs. So they're never solo or odd. There's always no imaginary zeros, or 2 or 4 or 6. It's always in pairs or none at all. So for instance, if you're told that a plus bi is a 0 of f, then automatically its conjugate, a minus bi, that's the conjugate. By changing the of the I term, you got the conjugate, is a 0 of f. No one is going to tell you this. So if someone tells you 2i is a 0, then definitely negative 2i is a 0. If someone tells you 1 minus I is a 0, then you should know that 1 plus I is a 0. They're always in pairs. They're always conjugate. Okay, number 42, page 294. It's a find polyfunction Q with degree 3 and zeros, negative 3 and plus I. Well, since the degree is 3, we know there's going to be 3 zeros. There's only 2 that were given, and since they were only given 2, we know if 1 plus I is a 0, then definitely what? 1 minus I is a 0. So we're going to have to write that down ourselves. They're not going to say. Okay, so to find, so they're not asking us to find the zeros. We're given the zeros. Unusual, because usually they tell us here's q of x, find the zeros. Okay, now they're giving us the zeros. find the original function. The degree is 3. For each 0, we get a factor. Remember the factor theorem? So x equal negative 3 is a 0. That means x minus 3 is a factor. Okay? And so the factors are x minus 3. So this would be my q of x. They're calling it q. The second factor, this is a 0. So x minus that. I'm going to put it in parentheses because it's two terms. And this is a 0. So x minus that is a factor. Okay? That's the c that we usually talk about. If c is a 0, x minus c is a factor. Now, it's not acceptable to leave your work like this. We need a polynomial function, so we want to work this out. So x minus 3, if I distribute the negative here, I would get x minus 1 minus I, and this would be minus 1 plus I. So if you treat this in term, a minus b, a plus b, the difference of two squares. So this would be x minus 1 squared minus I squared, a squared minus b squared. And now we can work it out. X1 squared is x squared minus 2x plus 1 because it's x minus 1 times x minus 1. And that's how we get. And then minus negative 1. So we get x minus 3, x squared minus 2x plus 2. And then you work it out. You multiply it out. And this is what you get. X cubed plus x squared minus 4x plus 6. So usually we're given this. And we're asked to find the zeros. Now we were given the zeros and we're asked to find the original function. Okay, so since I had three terms here, I distributed the negative to get the difference of two squares, x minus 1 minus I, x minus 1 plus I. So you can FOIL it, or you could do the difference of two squares. I did that because a minus b times a plus b is a squared minus b squared. It's just easier. And then I worked it out. Here's another one. Find a fourth degree polyfunction f that has the following zeros. There's always a test question like this, right? Negative 2, 2, so 2 real and 1 imaginary. And we know for every imaginary, its conjugate is also a 0. So 2i, so the conjugate is going to be minus 2i. Okay? The conjugate is going to be negative 2i. So we have to add that. So f of x is going to be for every 0 we get a factor. If negative 2 is a 0, then x minus negative 2, which is x plus 2, is a factor. X minus 2 is a factor. X minus 2i is a factor. And x minus negative, which is plus 2i, is a factor. So there's factors, therefore we're going to have a fourth degree. Okay, let's work the real and the imaginary together. This is the difference of two squares. If you FOIL it, it's going to be x squared minus 4. If you FOIL this, it's going to be x squared minus 4i squared. So x squared minus 4, that's plus 4, because negative 4 times negative 1. Don't ever forget that I squared is negative 1. And now if you work it out, it's x4 minus 16. Okay. Now let's look at 54, page 294. It says find all zeros. All meaning what? Real and imaginary. Okay, so we're back to finding the zeros. We're not given the zeros now. Okay, so we're back to what we did in the previous section, which is okay. So remember the method for doing this. We first list the rational zeros, possible rational zeros. P over Q. P is a factor of 9, so it's 1, 3, and 9. Q are the factors of 2. And then we list P over Q with a plus or minus. 1, 3, 9, and then 1 over 2, 3 over 2, 9 over 2, and it could be negative, okay? And then with the help of the calculator, we can narrow down our options so we can see which one we should do synthetic division. of 2x cubed minus 8x squared plus 9x minus 9. If we grab, oh, let me zoom that. This is, so we're gonna do zoom 6. And it looks like 3 is a 0. Let's check table. Is 3 a 0? Yep. So we're gonna divide by 3 using synthetic division. That's why it's important to know synthetic. It saves us a lot of work. Drop the 2. 3 times 2 is 6. Negative 8 plus 6 is negative 2. That's negative 6 plus 9. 9. Of course, the remainder has to be 0. Constant x squared. So p of x is going to be, since 3 is a 0 of p of x, x minus 3 is a factor, and the quotient is the other factor. Now, this is quadratic, so it doesn't look like we can factor it, so we can do the quadratic formula. 2x squared minus 2x plus 3 equals 0. The opposite of b plus or minus square root of the discriminant all over 2a. So that's 2 plus or minus b squared, negative 2 squared minus 4 times 2 times 3 all over 2 times 2. So 2 plus or minus, that's 4 minus 24, which is negative 20. So you can see that these zeros are imaginary. That's I root 20. So it's 2I root 5 over 4. So the two other imaginary are plus or minus I root 5. So the zeros are the first one that we got, and then are the imaginary ones. There's exactly 3 zeros because the degree is 3. One will show up on the graph, and the other 2 will not show up because they are imaginary zeros. Okay. All right. You can look at 62, page 294. It's solved on page 30 in your notes. Okay. So make sure you go over that. And that's all I wanted to do. No, actually, I wanted you to do 62, so I can do, I don't know, 60 or 64. I'll do 3 first. From page 294. So find all zeros of p of x, x to the 4 minus x squared plus 2x plus 2. So function, if we list p and q, p is factors of 2. That's perfect. We don't need a calculator actually, because there's only few of them. 1 over 1, 2 over 1. So plus or minus. So there's only 4 to check. If you try the calculator, so y equals x to the 4 minus x squared plus 2x and plus 2 well, it looks like negative 1 is a 0, and it has an even multiplicity because the graph bounces off at negative 1. Is negative 1 actually a 0? Yes, it is. Okay. So it bounces off there, so it looks like it's a multiplicity of even multiplicity. So if you want to divide by negative 1, there's x cubed that's missing, so we're going to put a 0 in there, okay? Make sure you don't forget that. So 1, 0, negative 1, 2, 2. Negative 1 times 1 is negative 1 plus 0. That's 1 plus negative 1. That's 0 plus 2. Negative 2 plus 2 is 0. So if negative 1 is a 0, then x plus 1 is a factor, and there's the other factor, remainder, constant, x squared, x cubed. So it's x cubed minus x squared plus 0x plus 2. So it looks like negative 1 again is a 0, so let's try that. 1, negative 1, 0, 2, divide by negative 1. That's -1, that's -2, 2 plus 0 is 2, perfect. So 0, constant x and x squared. So p of x equal, we already have x plus 1. Now -1 is a 0 of this, so x plus 1 is a factor and the other factor. And now using the quadratic formula, you should know how to do this by now. You get x equals plus or minus I. 1. So we got 2 imaginary and 2 real, but they're the same one, -1, -1. That's why the graph bounces off there. Okay, 66. Let's see what's in 66, page 76. 66, page 676. P of x equals x cubed minus 2x minus 4. 66. Page. I'm sorry, wrong page. Page 294. Okay, page 294. It says a polynomial is given factor into linear and irreduced quadratic factors with real coefficients and factor completely into linear and complex coefficients. So it says first factor it into linear and quadratic irreducible factors. Well, to factor it, we want to use the synthetic gen to find a 0 and then factor it. Well, if you use p over q, it's going to be 1, 2, or 4. If you do the graphing calculator, x cubed, just to see which one we should divide by first, minus 2x minus 4. It looks like 2 is a 0. Let's double check with the table. If we punch in the 2, do we get a 0? Yeah, so 2 is a 0. So let's do that. You divide by 2, so 1, and remember you're missing an x squared, so 0, -2, -4. 2 times 1 is 2, 0 plus 2 is 2, 2 times 2 is 4, that's a 2, 4, a 0. So since 2 is a 0, then x minus 2 is a factor, and that's constant, that's x squared. So this is irreducible quadratic factor, and this is linear. Okay, that's what they're asking for in part A. Now part B, it says completely factor into linear with complex coefficients. So they don't want any quadratic, they want all linear. So in order to do this, we're going to do the quadratic formula. X squared plus 2x plus 2 is 0. We're going to find those imaginary solutions. -2 plus or minus the root of b squared minus 4ac all over 2a. So it's -2, that's 4 minus 8, which is -4. So -2 plus or minus 2i over 2. So these are the two imaginary solutions. So now how do we factor that? So we have x equals -1 plus I and -1 minus I. So p of x, we have the linear factor that we already got. This is now going to factor into x minus this, and then x minus that. And we could work it out by distributing the negatives. So it's x minus 1 minus I, and then x plus 1 minus I. And that's what they wanted us to do. I'm sorry, this is x plus, x plus 1 minus, negative times negative is positive, okay? And that's it for 0.5 until 3.6. Have a good